Hi guys, welcome back to Data Every Day. Today we're looking at a data set of car accidents in the US with 3.5 million records. There's basically 49 columns, so we have quite a few features here. And it's all these different sort of statistics about a given car accident. What we're going to try to do is we're going to try to predict the severity of a given accident. So over here there's this right here, severity column, values 1 through 4, where 1 indicates the least impact and 4 indicates the most impact. I believe it's on the impact on traffic. That's how it's measured. So let's go into it. We're going to use a TensorFlow artificial neural network to make our predictions. And I'm importing NumPy and pandas to start. And then for pre-processing, we're just going to use the standard scalar and train test split function from sklearn. And then TensorFlow for our actual model. And that's all we'll need. It is a bit of a unclean data set, but we will be just fine. So let's load in the data using pandas.readcsv, and we can get the file path right over here. Now one thing I'm going to do is, because this is 3.5 million examples, it's just an unnecessarily large amount of data for our purposes. If we were training on a larger machine, or if we had a real reason to squeeze the most out of it, we would obviously want to use all the data we could. But for our purposes, I'm going to include this number of rows. I'm just going to limit it to 400,000, which is still a very large number of rows or examples that we can use. But this will just keep us, we're only using a fraction of the original data set. Otherwise, we'll run into all sorts of out-of-memory issues, and it'll just be really slow to process the data. Alright, so I'll load that in, and we'll take a look at it. And once we visualize it, I'm also going to get some info about it. So here's the data set, and you can see right away we can't see all the columns. There's this ... So I'm going to go into the console and type pandas.set option max columns. I'm going to set max columns to none. Now if we reload data, we can see all the columns now, all 49 columns. And we have 400,000 rows. So right away we notice that we have at least some missing values, and we have a whole lot of categorical variables as well. So I think the first thing we can do, you can see look, these two columns are completely null. So we'll just drop those, we know right away. But we can see there's a good number of in here that are don't have a single null value. So let's deal with those first. Let's deal with missing values. Let's get the so isNA gives us a data frame where true or false represents whether there's a missing value in that spot. And if we sum over the rows, we'll get the total number of missing values in each column. Now, I'm interested in not exactly the flat amount of missing values, but the percentage of missing values. To do that, we can do mean, because adding up the mean will just divide this number by 400,000 for each column. And now if a given one of these is over, let's say 25 to 30%, we're just going to drop that column, because at that point it's just it's too many missing values. So what I'll do is I'll make this null columns list, and we're just going to put in all the ones with really high missing values. These obviously have to go. This is both 100% missing, so it's end lat and end long. Whoops. End lat and end long for longitude. So those are both gone. This one has a 64% missing values, so we're going to drop number as well. Down here we have 85%, so we're going to drop wind chill. Let's see what else. This is just 1%, that's fine. 18%, we'll keep that one, but it's still a lot. 89%, this clearly has to go. There's just not enough useful information in these columns. 2%, and that looks good. I'll keep the 18% one. So we have these null columns. So a list of all the columns with too many null values. We're just going to say data equals data.drop null columns, and we're dropping from axis 1. So now let's take a look at the null values again. I guess we can do the mean. Some would be better here. Okay, so there's 74,000 missing values in this column. There's a whole number of things I could do to deal with these null values. We could certainly impute them based on the means of the columns, for all the numerical columns at least. Like, let's see, humidity, for example. Humidity, where is it? Here, is a percentage value. And anytime we have a null value in humidity, we could fill it in with the mean of the humidity column. And we wouldn't have too many problems doing that. Well, for the categorical features like airport code, we could simply one-hot encode this column, and then all the missing values would just have zeros in all the one-hot columns. So that wouldn't be a problem either. However, because we have so many examples, we have 400,000 rows. For the sake of time and effort, I'm just going to drop the rows with missing values. And we can tell from here that that will drop a total of 74,000 at least. But it will not be too substantial a number, because we have 400,000 examples. Now, I will just say I do not advise you to perform something like this if you really do care about the performance of your model. This is for educational purposes, obviously, so it's not so as important. But dropping rows is sort of like the last thing you want to do. If you can find other ways around it, it's a good idea to try to impute values or just encode them in ways that don't have to worry about missing values. But we're going to drop the rows here, and we have anytime we want to drop rows, we also should reset the index afterwards. And I'm going to include drop equals true, and this is because if we have drop equals false, it's going to use the old indices as a new column, and we don't want that. So now our total missing values, if we sum across rows and then again across columns, so let's print out total missing values, 0. We're totally filled in. And now let's see how many rows we have left. We still have 320,000 rows. So again, if we really cared about doing this properly, we would have gone through and tried to drop as few rows as possible. But in our case, this will work just fine. Okay, now there's a few more columns we want to drop. So let's do this. Unnecessary columns. So there's a lot of columns in here that are not helping us with our they're not helping us for our goal, which is let's predict the severity. And the way I'm going to figure this out is I'm going to create a dictionary. It's going to map a column to the length of the unique values in that column. That's for every column in data.columns if the data type of that column is an object. So these are all the categorical columns, right? Because I specified object only, which will be string values. And we're looking at this is the number of unique values in each column. And the problem with categorical columns is that if they're nominal features, having a huge number of unique values in it will give us a very large number of one-hot columns. And we don't, for example, well, take zip code, for example. The best way to, a possible way to encode zip code is one-hot encoding. But there are so many unique zip codes in here. Actually 57,000 unique zip codes in here. So that we would have 57,000 new columns added to our dataset. And that's going to be very taxing on the model that we're using. Having a huge number of columns is something it's good to avoid if you can, especially if it's not providing a tremendous amount of useful information. Now, you could also do something like a dense encoding of the zip codes, but what I'm going to do, just for our purposes, is I'm going to drop all of the very high, any of the features with a very high number of unique values. And I'm going to call those unneeded columns. There's also some in here that are just not useful at all. For example, like the ID, they're all unique, right? So it's not going to give us any information. So ID is going, start time and end time. Okay, these are not actually categorical, right? Because these are date and time features. So we'll hold on to those. We'll keep those. Let's see what else we have. So description and street. Description is not going to help us. We certainly could use it if we were really going to try to maximize the performance of this model. What we could do is use the words in the description as features and probably perform a dense encoding on the words. But we're just going to drop description for our purposes. Street. Yeah, okay, so there's 36,000 unique streets, and I'm just going to drop it because I don't want 36,000 new columns on my dataset. Side. Side has only three values, so that's a good one to keep. We're not going to do anything with that. City. City has 4,000, and that's sort of pushing it. Because we also have county and state, city is probably not so necessary. Again, there's definitely workarounds and ways to keep these columns and make it nicely, but I'm just doing this for the purposes of the video. I'm just trying to keep it simple. County will keep, that's only 548. 28 states, that's fine. Zip code we're going to drop, so there's just too many. Weather timestamp. Now we're not going to drop this because this is another date and time feature. And airport code is fine. Wind direction, that's fine. These all look pretty good now. Like, this is a reasonable amount of features to add. So pretty much anything with like over 1,000 new unique values I dropped, along with there's one more thing. So country actually has one unique value, and because this is a U.S. accidents, right? The country is always U.S., so it's just completely unnecessary. So let's drop that as well. And I think that's it. Data equals data.drop, unneeded columns, and we're dropping from axis 1. Alright, let's take a look at the data again. So now we have 38 columns, and these are all the features we're going to use. So, what to do now? Alright, I'm going to worry about these time and date columns now. And what I'll do is create these two little functions, one called getYears, that will take in a data frame and a column, and one will be called getMonths, taking a data frame and a column. And getYears is going to take one of these date and time columns and just return the year values from each example. To do that, very simple, we're just going to return the data frame indexed at that column with a lambda function applied to it. That's just going to take a date and return only the first 4 characters of the date. So it will return the first 4 characters, which is just the year, for each example in the column. Similarly, for the months, instead of the first 4, it will be the 5th through 7th characters. Well, actually, it'd be the 6th and 7th characters, which will just be the month. And then I'm going to apply these to each of the date time columns. So data, okay, no, what we'll do is get years. I'll give you an example. We pass in data and the start time column. It just takes the years from start time, right? Just the first 4 characters of each one. And so I'm going to make this a new column. We'll call it start time year. And I'm going to do this for all 3. I'm going to do years and months for both for start time, end time, and weather timestamp. And just for sake of time, I'll copy and paste this in. It just all, I did it twice, once for months, once for years for start time, and then again months and years for end time, and then again months and years for weather timestamp. And so now we'll have these 6 new columns, and we're going to drop the original 3 columns. Columns not defined. Oh, this should be column. Okay. So run that again. And if we take a look at the data again, whoops, we can see our timestamp columns are gone, but at the end we have these new 6 columns that are years and months for each of the original ones. All right, fantastic. So now we'll one-hot encode. So I'm going to create this function, one-hot encode. It's going to take in a data frame, a list of columns, and a list of prefixes to put on the dummy columns. We'll start by making a copy of our data frame. And for each column prefix pair in zip of columns and prefixes, so zip will just pair up these lists element-wise into tuples so that we can index them 2 at a time as column and prefix. And then I'm going to create a dummies data frame using pandas.getDummies, which will just get the dummy values for a given column and will include the prefix that we specify. And then we're going to concatenate the original data frame and the dummies side by side and store it in df. When we're done, we can just remove the original column from which we created the dummies, and we'll do that for each column, and then we'll return the data frame. Alright, so data equals one-hot encode. We'll pass in data, and our list of columns is going to be all of the categorical columns in here. So again, let me look back up at here. Okay, anything with 2 values, I don't have to do this to. I can use a simpler encoding scheme for that, which is just set one of the values to 1 and the other to 0. But for anything else, we're going to want to use one-hot encoding. So let's take another look at this. Alright, so side, county, state, time zone, airport code, wind direction, weather condition, and then the rest, these are all 2, and we don't have to use on those, and these are actually the ones that we created ourselves. I forgot to make them into numerical values, so they're coming up as objects, but these are actually not categorical. So this is everything we need right here. And then I'm going to include the list of prefixes, which how about we'll just do side for SI for side, CO for country, ST for state, TZ for time zone, AC for airport code, WD for wind direction, and WC for weather condition. Alright, we'll run that. and take a look at data, and we now have 1,300 columns, which is still manageable. Will be okay. They're all one-hot columns at the end. And then we have our original columns here. There are still a few binary columns in here we want to take care of. So these day and night ones, there's actually 4 of them. These 4 columns all have day or night as their values. So because they all use the same data, I can just make one function for it, which will be let's see, they're all twilight? No, and a sunset also. How about, we'll call it get binary column. That will take in data frame and a column. And how about if, because there's one in here called source, if a column equals source, then we're going to return df subcolumn with a lambda function applied that's going to map x, which would be one of these, to 1 if x is equals mapQuest, and otherwise 0. So mapQuest will go to 1, and the other value in here, which we take a look at it, actually not sure what it is mapQuest-bing. That will become 0. So mapQuest will be 1, and otherwise mapQuest-bing will be 0. And otherwise, this is, so if we're not dealing with the source column, that means we will be dealing with one of these here: sunrise, sunset, civil twilight, nautical twilight, astronomical twilight. We'll return df subcolumn dot apply a lambda function that maps x to 1 if x equals day, and otherwise if it's night will be 0. So this is just like a special case I'm including, so I can use the same feature, the same function on this and these 4 over here. All right. So we got our functions. So let's call get binary column, passing data, and then each one of these. So sunrise, sunset, and data sub sunrise, sunset equals the new column. Oh, this should be binary. Okay. And I'm just going to do this for each one. Let me just copy and paste it in. And at the top, I'm going to include the MapQuest one. What was it called? Source. So source, just going to do get binary of source. Okay. Alright, so I'll run this. And now, if we look at our data, everything is actually in numerical form except these true falses, but that's okay because I'm just going to cast the whole data frame to floats, and true will go to 1 and false will go to 0. So fantastic. Okay, let's begin splitting and scaling. So by splitting, I mean I'm going to split into x and y. Y is going to be what we're trying to predict, which is the severity of a given accident. So we'll paste in severity, and then we'll make a deep copy of it. And then x is going to be everything except severity. So what we're using to try to predict it. And we're dropping it from axis 1 and making a copy of that. And then I'm going to, I have to notice something. The unique values in y are actually 1 through 4, but TensorFlow requires that we start from 0. So all we have to do is say y equals y minus 1. And now if we look at the unique values, it'll be 0 through 3, which is what we want. Okay, x still looks like this, right? There's a bunch of true false in here, and in addition, I actually forgot to make these numbers, so these are still strings. So x equals x dot as type numpy dot float. So I'm just changing all of the values into floats. Alright, then I'm going to create a new standard scalar object from sklearn. And I'm going to scale x accordingly. This will give each column in x mean 0 and univariance, so that each column takes on a similar range of values as all the others. And then we're going to split again into train and test sets. So x train x test, y train y test equals train test split, passing in x, y, and giving it a train size of 70%. That'll include a random state as well. Okay, and with that, we're ready to train. So let's take a look at the shape of x. We have 1,344 features. So let's construct a model starting with an input layer with tf.keras.input. The shape will be a vector of length x.shape sub 1. So vector of length 1,344. Alright, and then we'll have two hidden layers, dense layers, give 64 activations, pass in inputs here, and then I'll have another one, but I'll pass in x. Then our output layer will just be another dense layer, but it's going to have 4 activations, one for each class, and a softmax activation function that will give each of these 4 values, value between 0 and 1, which will be the probability estimates for each class. And I'll pass in x. And then model equals tf.keras.model, and I'll pass in inputs and outputs. Then we'll compile the model. We'll use an atom optimizer, sparse categorical cross entropy for our loss. And for our metrics, we'll just use accuracy. Alright, we'll set up a batch size and epochs. And we'll store our model's fit history in history. We're training on the train set, x train, y train. Let's give it a validation split of 20%. Pass in the batch size and epochs. And let's also include some callback functions. So one callback I'll use is reduce learning rate on plateau. That will just, when we see that the loss is not improving, we'll just reduce the learning rate. And then furthermore, we'll also have early stopping, which even after reducing the learning rate, which will hopefully allow us to converge nicely, we still, if we see that the loss is still not improving, we're going to stop after the validation loss has not improved for 3 epochs. So patience is how long we're willing to wait before stopping, and this is the value we want to track. And then once we stop, we're going to restore the best weights of our model from the best epoch. Alright, let's run that. And when we're done, we will evaluate the model. Here I'll print out test accuracy and model.evaluate on the test set. I'll turn off verbose, and then I'll just get 1, which will give us the accuracy value. Alright, so it stopped after 8 epochs, and let's get a look at how it did on the test set. Oh, sorry, this equals 0. And we finished with an accuracy of 81%, which is fairly good, especially considering how much information we had to drop from our original dataset. First of all, we only used this fraction of the data, and we ended up dropping a large number of both columns and rows. But all in all, I think this is pretty good, and that will wrap up today's video. thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.